please briefly summarize your education and professional background, and what is your new role at ERVA?
So I'm Spike Narayan. I have a STEM background and a PhD from Lehigh University in material science and engineering. And then I worked at IBM for 41 years following that. And I just retired very recently. And so ERVA approached me about this interim position. And the reason why it's interim is because I just retired and I haven't quite figured out what I want to do. So I said, okay, let me give it a shot. And so that's where I am.
So what were you doing at IBM's California Research Lab, and how will that influence your role at ERVA?
Oh, that's a great question. So in the California lab, I had several roles. The most recent role was running the whole lab. The IBM Research is a very, I guess, very focused organization with a very broad agenda. As you know, IBM has a very broad interest in many products. So from AI to quantum computing to all kinds of exploratory science and physics and chemistry. So it spans the gamut of technologies that we feel important to bring to market. So in terms of my own views of my role at IBM, it gave me a wonderful opportunity to take ideas that are birthed in a research lab and translate that to products and offerings that IBM would have. So it's translation research and exploratory research. I think the combination is a very powerful combination. And I think exactly what ERVA is looking to see is how do you actually identify and develop bold ideas that are innovative.
Okay, thanks. Just to clarify, ERVA is the Engineering Research Visioning Alliance. And what would you describe their role in the engineering community, and how do you help plan on developing that role further?
So their role is a very interesting one. As you know, it's an initiative and funded by NSF, and I think it's a new role that NSF is trying to kind of figure out. And it is, how do you get the engineering community to look out 10, 20, 30, 40 years out in time, right? Because if you look around you, there are lots of global challenges, societal challenges in terms of water, energy, healthcare, and you can just go on and on and on, right? And in all of these areas, I think the engineering community needs to be involved. They need to be kind of futuristic in how they look at their role. And what ERVA is trying to do is actually identify and develop these transformative ideas and also help catalyze the engineering community to kind of in the pursuit of innovation in some sense and figure out what kind of research they need to do to have a high impact many years down the road. And what I would like to do in this role is help figure out how to develop these ideas better, how to get the engineering community involved in a better way. And so it's a learning experiment when learning as we go.
I understand that when you're working at the IBM lab, you're working with AI, semiconductors, and quantum computing. Do you think that those have a role that can fit into the future of engineering?
Oh, absolutely. In fact, one of the great things about futurist thinking is it's always cross-disciplinary. It's never confined to one department in a university or an industrial lab. And what we did at IBM was all about cross-disciplinary research. So the training that I have is really trying to figure out how do you get computer scientists to work with physicists and chemists and things like this. And if you look at all of the topics that ERVA is starting to look at, they all involve very multidisciplinary teams. And so I think trying to figure out how to speak the languages of very different engineering or scientific communities is part of the game.
Could you go a little bit into the specifics about what some of these things might look like? Even though I know you're new to ERVA, but maybe you could say how you did that at the IBM Research Lab and like take me through a little bit of specifically what this might look like and what you have in mind.
So if you look at research ideas, right? Research ideas are born in a lab where you do an experiment with a beaker and you come out with, hey, aha moment. But then taking it from a lab and a beaker where you do things at, say, 5 milliliters or half a milliliter scale to something that you have to do in tons and liters, that translation work is mostly engineering. And I think that is where a lot of the innovation happens in the industry is trying to figure out how do you take a phenomenon that you have observed or invented in the lab, and how do you actually make it a useful commodity in the marketplace. And this translation research is a fascinating area. And I think that is where I think the engineering community can be very, very useful in looking at some of these global challenges. And I'm hoping that the recommendations that ERVA comes out with can actually be implemented by the engineering community going forward. So they have all the tools and talent.
Could you describe like one specific example of something concrete that maybe I or other engineers can relate to, like something that you worked on in the past or something that might be coming up?
Sure. I can give you a past example from IBM since I haven't been in ERVA that long. So many years ago, maybe 7 or 8 years ago, we started looking at the role of catalysis in chemistry, uh, and specifically catalysis where heavy metals are not used. As you know, today the petroleum industry uses catalysts a lot, but it's all platinum and other heavy metals. In the semiconductor industry, heavy metals is a no-no. You cannot have heavy metals because it'll destroy a lot of the processes that you have in the semiconductor fab. So what we did was we set out to work with Stanford in this case, one researcher and one professor, to explore how can you do catalysis without heavy metals. And they actually were responsible for starting a whole new field of research called organocatalysis, basically using organic molecules to catalyze chemical reactions. And what this actually yielded a few years ago is a methodology to recycle plastics. Who would have thought 5 years ago that we invented organocatalysis and the end result would be addressing a very major global challenge like recycling plastic? So we were able to take this catalyst that we invented for the semiconductor space and take PET bottles, waste bottles, and reduce them to their original state and then use it again. So completely close the loop on plastic recycling. Fascinating example that I wanted to give you.
Yeah, no, that's great. And how long approximately did that kind of research go from like idea to the research to finding out something successful and to having a goal to reach for?
So I would say probably 5, 6 years, something like that.
And would that be someone specifically dedicated to that, or do people work on this while conducting other related research?
So it's usually people always work on 5, 6 different things, right? They have something that they do for the semiconductors, and then they may have 10, 20% of the time devoted to really exploratory stuff. And this would start out in the purely exploratory phase and then graduate to something that's more relevant for what the company needs and for the world.
In your past or current experience, do you find it a struggle to convince, engineers who are used to, doing this engineering work is what matters and you got to get the job done to understand and appreciate the importance of doing the research?
No, in fact, I think there is an art to this. It's not really a science, and the art is involving the engineering community early on in the discovery process. So they have a sense of ownership, and so they're really motivated to take their idea to the marketplace as well, right? So that's how you can engage the community early. You have to respect their skills. Their skills are different from the skills of scientists, both equally important, but both need ownership.
Again, could you describe a little bit like in a specific example of what that might look like to make that persuasion, that connection?
So, for example, once we discover, like in this case, the catalyst example, we would actually go to different funding agencies and ask them if they're interested in creating a process to recycle plastic. And this conversation would obviously happen with engineers in the room because they're the ones that know how to take this and build a pilot plant and take it to market. So the scientists and the engineers would approach companies that have waste plastic, right? Soda companies, for example. Increasingly, athletic gear is all polyester. All these uh, performance shirts and pants that you see today in the sporting space, they're all polyester and can all be recycled. And so we would go out to all of these folks, have a conversation, and start a research program around them. This is what we actually did.
All right, that's a fascinating example. So, are there any specific key elements of good engineering research, and would they be any different from other areas of scientific research, or are they more similar?
I would say there are a lot of similarities, but there are some contrasting differences between, say, scientific research and engineering research. In the scientific space, you're always kind of exploring with no real process or method in mind. It's try this, try that, and see what works. In the engineering space, there's a little bit more rigor. You have a process, you have a modeling method, you have a simulation way of doing things, you have a way of unearthing issues, you have a way of solving problems along the way. And so you have much more of a process and a method when it comes to engineering than we do in the science. Science is a little bit more, let's see what happens. Engineering, you have a commitment, you have an end goal that is very clear. You have to build a bridge. You're not dreaming about what a bridge might look like. You just have a drawing and you go from it to build a bridge, right? So you have a process and a method, which I think is the big difference between engineering and science.
And is the engineering research typically like science research in a university or in a lab like yours, or can people do that out in their offices and in their fields? Is there such a thing as like a commercial engineering research divisions?
Well, it depends on the field, right? Like, for example, if you're talking about civil engineering, you cannot be sitting in your office and doing research other than doing some modeling, perhaps, right? In the area of computer science, you could probably be sitting in your office and playing around with algorithms and so on. So it depends very much on the field, the kind of capital investment one needs to do the work. That's what usually differentiates various kinds of fields of study.
So are these groups, the researchers and the field engineers typically separate and doing different things? And then how do they come together to create final products?
Yeah, so I think this is where the structure of the organization is very important. You could have a very insular research division where they just create ideas and throw it over the wall, or you could have a highly collaborative environment. And I think the success of the company or the organization depends to a large extent on how well the engineering community and the scientific community can integrate it into research groups and goals and milestones and the like.
Okay, just to kind of fill out the picture, can you describe some good examples in your opinion of engineering research that has positively affected the engineering field? Perhaps some of your own work. I believe I read that you have 50 patents or something like that.
Sure. Yeah. So that's a fun question because I can go on for an hour, but let me just take one example to make the case. Right? So I don't know how familiar you are with DRAM technology. It's the memory module that semiconductor companies have been making for decades, right? So way back in the 80s and in the early 90s, as Moore's law was really driving this whole miniaturization process in a gung-ho way, we realized that the DRAM technology was seriously being limited by one process step. And that had to do with using lasers to increase the yield of DRAM products. And because when you use a laser, you're limited by the wavelength of the laser, you cannot shrink those dimensions of what used to call fuses in those days. Fuses are basically changing a circuit on the fly, deleting a line and adding a line in a different way, right? So you could not delete lines that are too much smaller than the wavelength of the laser that you're using to delete. So we came up against a problem of trying to shrink these Moore's law kinds of dimensions and yet have a robust process to increase the yield of DRAM. And so in one of the series of patents that I have, it has to do with what is called electrical fusing. So eliminate the laser completely and use electrical pulses to actually melt a line and sever the line as opposed to coming down to the laser and blasting it so that you're no longer limited by the physics of light. And no matter how small your electrical line is, you can just go and fuse it and move right on. And that helped the whole DRAM industry kind of move into the Moore's law regimen, right? And in fact, I think every DRAM that is made today has eFuse in it, electrical fuse. That's just one example where science and engineering come together.
All right, that's a great example. And so how did you come up with that idea? I don't even you don't have a ton of time, but I think we can talk a little bit about, where'd that go from an idea to and how long did it take to develop and to reach into the final products?
So I would say this was fairly rapid. I would say in less than 3 years, we actually qualified a product going from an idea in the lab. And to accelerate the process, I did something somewhat unique, which most people don't do. And that is, I actually left the research division, went into the DRAM product division, and decided to kind of help the team there with the whole process of developing it and not just being in research and giving it to them, right? So I actually stayed engaged for 3 years, worked with the team, developed it, qualified a product, and then came back to the research division. So this kind of made it much faster than it normally would. And usually, not everybody who does research is interested in taking it and doing an engineering exercise with it. In this case, I just happened to be interested. So I did the research and also helped with the engineering. So it was a very, very fun experience and also sped up the whole process, I would say, maybe 2x, 3x, I don't know.
All right, that could be great advice for somebody considering doing the same thing. And this was all at the IBM Research Lab, is that correct?
Yeah, this was when I was back in New York Research Lab.
Okay, so I read in your background that I know some makes sense with AI, semiconductors, but also mentions quantum computing. How do you think that could fit into the engineering? I'm just curious for myself on that one.
So quantum computing is just a way of doing computation, right? So today we do computation on big servers, mainframes, and the like. And there are some intractable problems in the sciences. There are many actually. And the way we solve them today is by approximating it and then bringing it down to a form factor, which today's supercomputers can maybe take a crack at it. It may spend maybe hours or days, but they can get the job done eventually. But there are some problems where you really cannot solve it because they are what they call NP hard problems in computer science. And so these solutions don't exist in the offerings that we have for supercomputers. So you necessarily need a different computing paradigm to solve some of these problems. And these are typically complex problems where it's very multidimensional problem. I'll give you one classic example, weather. Weather is one of the most challenging things to model. And I think today's computers are at their limit to solve problems. And still, we don't get it right, as you know, right? And so quantum computing can start addressing some of these really, really hard problems. It doesn't mean quantum computing will replace existing computing in the future. It just means for some classes of problems, they can actually they can solve the problem while the existing computers cannot. So you selectively use a combination of quantum computing and conventional computing down the road. So it's just a way of doing the calculations, doing the models. You can do the models at bigger scales. You can have many more elements in your modeling that you can do, so you can be more thorough and more accurate in your analysis. That's really what quantum computing will let you do at scale. So I just want to kind of leave you with this one thought is that engaging the engineering community, having them think 10 or 20 or 30 years out is a fascinating area and it's a challenging area. And I think ERVA is trying to get into the space and really have a big impact on solving some of these global challenges. And that's why we take this whole idea of identifying and developing some of these ideas and coming up with solid, actionable recommendations is very, very important, not just for NSF and other engineering or other agencies to kind of help with, but also for the engineering communities to take on some of these challenges and really address them head on. Right? So it's a very exciting period, and I'm glad NSF is actually involved in the space, and ERVA is kind of the I would say diverse, inclusive partnership that's helping get this going.
And is what you described going to be your focus and now in your new interim role?
Oh, absolutely. Yeah, absolutely a focus. Yes.
And do you have a time limit on when you're going to decide if this is interim or not, or are you just going to see how it goes?
Oh, so I'm just barely 3 weeks into it. So I think I need a few months to figure out what I want to do after I retire. And so I think in a few months, maybe I'll know better.